Who are the coolest elements on the periodic table? When I say the coolest, meaning that everybody wants to look like them. Noble gases. So, and if you look, that's going to be the nature of the octet rule. Everybody wants to look like a noble gas. So if we look at sodium, how many valence electrons does sodium have? In alkali metal, he's only got one. And so we could draw what we call a Lewis dot structure for sodium that shows only the valence electrons as dots. And we typically fill them in, one on each side for 4 different sides, and then doubling them up if we have more. Now chlorine, on the other hand, how many valence electrons does chlorine have? Good. Right before the noble gases, 1, 2, 3, 4, 5, 6, 7. Does either one of these have a filled octet for its valence shell? No. Sodium's like, woe is me, woe is me. If I didn't have that electron, then my previous shell would be completely full, and I'd have a filled octet. And so sodium, being a metal, they commonly do what? Not share. They lose electrons easily because they have very low ionization energies. Would it be true if I said that metals like to lose electrons, that they like to? Well, no. Nobody wants to lose any, usually, because it's still going to cost energy. It's just it costs the least amount for them. If somebody's going to lose an electron, sodium's like, well, if somebody's got to do it, I guess I could be the one. So, however, chlorine, non-metal, he's like, dude, woe is me, if I only had one more electron. And so he wants to do electron affinity instead, wants to gain electrons. And so in this case, the magical solution here is that sodium's electron gets donated to chlorine, or chlorine steals it, however you want to look at it. And the net result here is that now sodium, losing that one valence electron, his previous shell is full though. And so now he kind of has a filled octet. He looks like a noble gas in terms of electronic configuration. Chlorine, on the other hand, gaining an 8th electron, now has a filled octet as well. But now we have charges. Sodium lost an electron, so sodium has a positive charge. Chlorine gained an electron, so now chlorine has a negative charge. And the interaction between a positive and a negative ion is called an ionic bond. There's your ionic bond. And again, the goal here is that so that both atoms could satisfy the octet rule. And so here, with a metal and a nonmetal, a transfer of electrons allows them to satisfy the octet rule. And so the octet rule is kind of the nature of most ionic bonding, at least the stuff we'll talk about in this class. However, what if I had 2 chlorine atoms instead? And this chlorine atom is, woe is me, I wish I had another electron. And this chlorine's like, woe is me, I wish I had another electron. And this chlorine's like, give me your electron. And this chlorine's like, screw you, give me your electron. And they just go back and forth, screw you, give me yours. And nobody's willing to give an electron, right? Because nonmetals like to gain electrons. Out of anybody, nobody really wants to lose electrons, but the nonmetals really are not willing typically to lose an electron. Good luck. And so what's the solution here? They're going to share them. It's like, okay, I'll put mine in, you put yours in, and we'll share some electrons and form a covalent bond instead. And so those 2 electrons are shared. And we typically draw that instead as what? Yeah, let's put a big fat line in there. And that line represents the 2 shared electrons. And the shared electrons, that's a covalent bond. Yeah, it's really 2 electrons. We just start drawing lines for covalent bonds instead. But again, the goal here is that this chlorine says, yep, I got 2, 4, 6, 8 electrons around me. And this chlorine says, yep, I got 2, 4, 6, 8 electrons around me. And both of them get to say that they have a filled octet and obey the octet rule. So the octet rule is not only the nature kind of ionic bonding, but the nature of covalent bonding as well. Now we should talk about a couple of octet rule violations or exceptions, if you will. So we've just seen a couple examples where they follow the rules. So before we get too far into drawing Lewis structures and stuff, talk about a couple exceptions. So there are a couple exceptions that go under the octet rule. So hydrogen does not want a filled octet. Hydrogen wants to look like helium. How many valence electrons does helium have? Just 2. So hydrogen's like, I don't want 8, I just want 2. So you'll see boron and aluminum thrown into the mix here. And so how many valence electrons does boron have? And I wish I had a periodic table here. So, but aluminum here, so sodium, magnesium, aluminum has 3 valence electrons. So does boron. Boron's right above him on the periodic table. And so if you look, having 3 valence electrons, they're like, I'll share one of them with you, and I'll share one of them with you, and I'll share one of them with you. And they end up with 3 bonds, and only a total of how many total electrons around them? 6. And they're like, well, that's all I could do, I guess. And so boron and aluminum routinely violate the octet rule and are typically happy with only 6 valence electrons. And I'll use that word happy kind of loosely here. The one you may or may never see is beryllium. Beryllium only has 2 valence electrons, and so if you ever see him involved in making a covalent compound, you'll see him typically only making 2 bonds and having a total of 4. But the most common exceptions that go under the octet rule are by far hydrogen and boron. Those are the ones I usually look for first. Aluminum, kind of metallic. Beryllium's a little bit more metallic, and so they're not so likely to actually form covalent bonds, but whatever. Cool, then you got elements that can exceed or go over the octet rule. Now the first rule, for those that went under, this is what they normally do. Hydrogen, boron, aluminum, beryllium, they normally don't obey the octet rule. But here, rule number 2 is a little bit different. These are the ones that can go over the periodic table. They don't have to, but they can. In this case, it's typically your 3rd row elements and lower on the periodic table. So if you look, it's kind of like, I've got the 3rd row up here. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. The 3rd row and lower. 2nd row up here, or the 1st row, they can't do it. It's only the 3rd row and lower. Where does the octet rule even come from? What's so magical about 8? Well, the noble gases have 8, but why 8? What's so great about 8 electrons? Well, if you recall, it's 1s2, but after that, 2s2 and 2p6. The entire shell can hold 8 electrons. It's a full shell. But notice, once you get to the 3rd shell, there's not just s orbitals and p orbitals. What else is there? Starting at the 3rd shell, d's. And as a result, if you're in the 3rd row or lower, if you got more than 8 electrons, well, okay, great, I'll just pop them in the d orbitals then. I don't have to, but if I have extras, great, whatever. And that's why the 3rd row and lower is allowed to go over the octet rule. The 2nd row can't go over because they don't have d orbitals in the 2nd shell. They'll only start in the 3rd shell. Cool. And then your last example of an octet rule exception. If you have an odd number of total electrons, or total valence electrons anyways. If you've got an odd total number of electrons, well, if everybody has 8, add up you're going to be adding even numbers and you have to get an even number. But if they have an odd over, if a molecule has a total number of electrons is odd, you can't get everybody a filled octet. It's impossible. This happens very rarely though. So not the most likely exception, but these 2 happen all the time and you got to recognize examples of both. So if you look, there's really 2 ways to learn how to do Lewis structures. As long as we're not going here. So then the way which Dr. Briggs taught you about looking at electrons has and electrons wanted works. But if you're in one of these cases where somebody's going over the octet rule, that way doesn't work. And you have to use the other way. Whereas most classes just use the other way all the time. So you have to learn both ways in his class. You got to learn the has and wanted, which in principle I like that way better, but that way doesn't always work, and so you have to learn the other way for this. Because you have to learn the other way anyways, I'm only going to teach you the other way. I'll probably do one example with the has and wanted way, but do the rest the other way because you have to know it anyways. So and learning two ways is not so helpful most times for students. It's just like, well, if I got to learn two ways anyways, why not just learn one? But, so here's the deal. Let's start out with something simple. We'll talk about Lewis structures. And again, we kind of looked at a couple of Lewis dot structures already. You know, the examples we did with NaCl and Cl2 molecules and stuff like that. So we've already kind of set the groundwork here. So, but Lewis structures or Lewis dot structures only contain the valence electrons. So, and if you look on the periodic table, you know, the first row or the first group, they have one valence electron. The second group, the alkaline earth metals, have two. Boron's column, the third group, has 3 valence electrons. Carbon's column has 4. Nitrogen's column has 5. Oxygen's column has 6. Fluorine's column has 7. And the noble gases have 8. That's kind of where it works. So how many valence electrons does carbon have? You know what? Let's do one more thing here, actually, and make this just a little bit easier. Got one? Okay. Cool. I'll leave this one up here for the fun of it as well. So how many valence electrons does carbon have? 4. Sweet. So with 4 valence electrons here, what about hydrogen? 1 each. With 4 of them, that's 4 more, so a total of 8 valence electrons. So again, 2 approaches to this. So if we do this the Briggs way, we've got a little column here. We've got wanted, has. So does carbon want a filled octet? Sweet, then he wants 8 electrons. So does hydrogen, in this case, want a filled octet? No. How many does hydrogen actually want? Just 2. So 2, 2, 2, 2. Sweet. How many valence electrons does carbon actually have now? 4. And hydrogen's? 1 each. So if you notice, we've added up the valence electrons, got 8. That's what the has column ultimately tells you. Okay, but the wanted column, so in this case, 8 plus 2 is 10, plus 2 is 12, 14, 16. And so we want a total of 16 electrons. We only have 8. And so what it tells me, though, is then I need some shared electrons that both atoms will get to count. And the difference between these two is how many shared electrons I need. And so in this, how many shared electrons am I going to need? 8. But how many electrons are in a bond? 2. And so I'll take the total number of shared electrons and divide by 2, and this should get me the number of bonds. And so in this case, we see that, yep, this structure is going to have 4 bonds. Okay, so, and this is one way to go about it. This is probably the last time I'll use this, but did want to set it up once. In this case, who's the central atom? Well, it's carbon. How do you know? It's not because there's only one of them. It's because he can make the most bonds. And so in this case, he is going to be carbon in the middle. We are going to surround him with some hydrogens in this case. And if you look at why this is again, notice the atom in the middle has to make the most bonds. So then you better put the atom in the middle who can make the most bonds. And so if you look at this, how many more valence electrons does fluorine need to have a filled octet? 1. That's why fluorine typically makes 1 bond. How many more electrons does oxygen need to be happy? 2. So that's why oxygen typically makes 2 bonds. How many more electrons does nitrogen need to be happy, I should say? 3. So he typically makes 3 bonds. Carbon? 4. Boron? Careful. How many electrons does boron want? Not a filled octet. So how many more does boron really need to get to a total of 6? 3 more. And so it goes from 1 bond, 2 bonds, 3 bonds, 4 bonds, back down to 3 bonds for boron. So you want to put the guy in the middle who can make the most bonds. But we got to remember that once you get to the 3rd row and lower, the typical number doesn't always apply because they may go over the octet rule and just break everything apart, anyways, as far as the octet rule goes. So, but in this case, carbon can make typically 4 bonds. Hydrogen only 1. We'll definitely put carbon in the middle. He can make more bonds. And in the middle, he'll have to. And start, in this case, with 4 total bonds. You just added in 4 bonds. Great. 1 there, 1 there, 1 there, 1 there. We're done. That is CH4. Fill in, at this point, any non-bonding pairs. Now, that's the wanted has method. But the other way you're going to have to go here, and this way you're going to have to learn anyways, and so it's the way I'm going to present from here on out, is set up your skeleton. Put the atom in the middle. So who can make the most bonds? Don't even go here. Go straight to total valence electrons. Set everything up with at least a single bond. If they're going to be in the structure, they got to at least be single bonded together. And from that point, fill up the outside atoms. Well, they're already full. Any leftover electrons would then go to the central atom. And once you're out of electrons, and we are out, then you ask yourself, is the central atom happy? And he's happy, and this is the structure. But I want to start out with the most basic of structures, and we'll definitely make this harder from here on out. So we'll look at ammonia. How many total valence electrons in ammonia? So nitrogen's got 5, each of the hydrogens has 1, and that adds up to? Cool. Who goes in the middle? Nitrogen. And again, we'll set up the skeleton with all single bonds. And then I fill up the outside atoms. How many more electrons does he need, the hydrogen? He's full, he's full, he's full. Okay. Any leftover electrons then go on the central atom at that point. Do I have any leftover electrons? Yeah, I got 2 left. So the central atom gets them as a non-bonding pair. Cool, and now I'm out of electrons. And once you run out of electrons, the last thing you ask yourself, because you always fill up the outside atoms first and worry about the central atom last, the last thing you got to ask yourself when you run out of electrons then is the central atom happy? And is he happy? Yeah. Yes, then that's the structure. That is the Lewis dot structure of ammonia. Done. Let's look at HCN. And again, had you done the whole has and wanted thing here, it would have worked here as well. So HCN, how many total valence electrons for HCN? Hydrogen's got 1, carbon's got 4, nitrogen's got 5 for a grand total of 10. Who can make the most bonds? Carbon can. Hydrogen typically only makes 1, carbon typically makes 4, nitrogen typically makes 3, carbon wins. So carbon goes in the middle. And start it with all single bonds. And then where do I put electrons first? Fill up who? Outside atoms. Does hydrogen need any more? Nope, but nitrogen needs more. And you'll always have enough to fill up the outside atoms, so just fill them up. And now, if you have any leftover electrons, we'll then give them to the central atom. Do I have any more electrons? No. I've used 2, 4, 6, 8, 10, I'm out. And the last question you got to ask yourself then once you run out is the central atom happy? Is he happy? No, then somebody's going to have to share. Well, hydrogen doesn't have anything to share, so it can't be him. It has to be nitrogen. And share 1 pair at a time. So I took away one of his lone pairs, shared. Is carbon happy now?
How do you determine if it's happy or not?
Ooh, happy means that it followed the octet rule. And so let's go back a step here. Is carbon obeying the octet rule? Is he happy? Notice he only got 2, 4 around him total. No, he's not happy. He needs a total of 8 to obey the octet rule in this case. And again, does everybody always obey the octet rule? No. And so happy means, do they have the normal number they want? So in boron's case, it wouldn't be about getting 8, it would be about getting 6. But carbon, he wants a filled octet, and he don't have it. So nitrogen over here is going to have to take one of his non-bonding pairs and share it with carbon. Is carbon happy now? No. So we'll take another pair and share again. Is carbon happy now? Yes, that's the structure of HCN. And so notice, in this manner of drawing Lewis structures, the double or triple bonds come from when the central atom's not happy. Because again, we worry about filling up the outside atoms first with this convention. And if the central atom's not happy when you run out, then you give them double and triple bonds if necessary. So that's HCN. Let's look at carbon dioxide. How many total valence electrons in CO2? Got 4 for carbon. Oxygen has 6 each. 2 times 6 is 12, plus 4 is 16. Who can make the most bonds? Carbon, so carbon goes in the middle. And so in this case, all single bonds. Where do I put electrons next? On the outside. Fill them up. And again, you'll always have enough electrons to fill up the outside atoms. Oxygen wants a filled octet, so I'm going to give it to him. Do I have any more electrons for the central atom left over at this point? Well, there's 8. There's 8, and I'm out. I've used all 16. Is carbon happy? No. So what do I got to do? Share. And in this case, they're equivalent, so it doesn't really matter who shares first. Okay, I'll have this oxygen share first. Okay, is carbon happy now? No, so I need to share again. Now I got a problem. Does this oxygen share, or does this oxygen share? Why? To make it even. Is there an even rule? So it turns out there's no even rule. There's no symmetry rule. You might be like, Chad, have him share, because then it's symmetrical, and I like symmetry. I'm totally OCD, and that's what I want to see. So if I have a piece of paper on the left side of my desk, I got to put one on the right side too. You know that. Well, notice I could have drawn and given this side, had this oxygen share both pairs and only have one left, and have this one not share at all. And it doesn't look even, but there's no even rule, it turns out. And so the rule actually turns out to be what we call formal charge. When you have two different ways with different bonding arrangements to get a structure, formal charge will tell you which one is better. And so in this case, the way this works, there's a technical mathematical definition for formal charge, right? If you recall, maybe, formal charge was equal to the normal number of valence electrons minus non-bonding electrons minus half the bonding electrons. How likely do you think you are when you wake up tomorrow morning to remember that formula? Cool, so we're not going to use that formula. We're going to use the formula of take the normal number of valence electrons. Great, what's oxygen's normal number? 6, minus the number of dots and lines around him. So normal number minus dots and lines. So in this case, how many dots? 4. How many lines? 2. So normal number for oxygen of valence electrons is? Oh, no, what's the normal? Just start with the 6 minus 1, 2, 3, 4, 5, 6, and his formal charge is 0. Okay, so big zilch there. What's and same thing on this oxygen too, notice the same calculation. What's carbon's normal number of valence electrons? 4. No dots, but 4 lines, and 4 minus 4 is 0. Okay, let's go here. If we look at carbon first, you're still going to do 4 minus 1, 2, 3, 4. Still 0. But for this oxygen, it's going to be 6 minus 2 dots, 3 lines. So 6 minus 5 plus 1. And here, 6 minus 1 line, 6 dots. So 6 minus 7 minus 1. And so here, we assign the formal charges. Now you know how to do it. Hopefully that's a formula you can remember. But the key is this. You want formal charges as close to 0 as possible and as few as possible. So you don't want formal charges. 0 is the best. And the closer to 0 is the best. And so in this case, when I look at the two structures, this one by far is superior based on formal charges. Not based on being even, but based on formal charges. So let's just pretend for a moment you have a teacher who, let's say, is from San Diego, or at least went to college in San Diego. Say he's a Padres fan, and he is. And let's just pretend that the Padres suck this year. Oh, wait, they do. So let's just say he's not happy when he writes your exam this weekend because Padres aren't doing so hot. And so he gives you, give me his Lewis structure. This is a doubly tricky question. If I want to give you a hard one, this is the one I'm going to give you. So how many total valence electrons in N2O?
16.
Good. 5 times 2 is 10, plus 6 is 16. Cool. Who goes in the middle?
Nitrogen.
Good. It's not the one that there's only one of, because who can make more bonds, nitrogen or oxygen? Nitrogen can, and so nitrogen goes in the middle here. So you got an oxygen on one side, the other nitrogen on the other side. That's the first thing that makes this tricky. Most students try to put the O in the middle. Doesn't go there. Cool. Where do I put electrons first? Outside atoms. I'm going to fill them up. And here we have the dilemma. So how many, I'm out of electrons, by the way, and I ask myself what? Is the central atom happy? Is he happy? No. How many more electrons does he need? He needs 4 more. He needs two atoms to share. Well, again, there's 3 ways to do that. Either he shares twice, or they both share once. And again, there's no such thing as an even rule. So we got to consider all possibilities. So in this case, the nitrogen on the left could share twice. Doesn't seem very fair. But again, there's no fairness or even rule. The oxygen could share twice. Or they could both, outside atoms could share once. And so we now have 3 possible structures. And there's one best structure, and it's all based on formal charge again. And so if we look here, if we look at the first structure, so how many valence electrons does nitrogen normally have? 5. What's the formal charge here? 5 minus 2, 3, 4, 5 is indeed 0. Awesome. What's the formal charge for this nitrogen? Not 0 in this case. 5 minus 4 is plus 1. And what about this oxygen right here? Normal number is 6 minus 1 line and 6 dots, so 6 minus 7 is -1. Not looking so good for him. Turns out he's the right structure, as we'll see, though. So what about here, nitrogen? 5 minus 7. Ooh, -2 charge. That's terrible. So he's probably going to lose. What about this nitrogen here? Plus 1, 5 minus 4. And the oxygen here? Yeah, 6 minus 1, 2, 3, 4, 5 is plus 1. Cool. Last but not least, we've got here. So nitrogen, 5 minus 6 is -1. This nitrogen, 5 minus 4 is plus 1. And oxygen, 6 minus 6 is 0. Okay, so which one for sure loses this battle here? Middle one, he loses. He's got the worst formal charges. He's got 3 different formal charges, and they're farther away from 0. So we're going to get rid of this one right off the bat. He's the worst structure we could have drawn. But between these two, which one's got the fewest number of formal charges? Well, the tie, okay. Which one's got the formal charges that are closest to 0? Well, 1 plus, 1 minus, 1 plus, 1 minus. It's still a tie. Okay, then we have to look at the best location for the charges. Well, notice, which charge do they have in common in the same location? The plus charge on the central atom. The central nitrogen has the plus charge. The difference then is where the negative charge is, on oxygen or on nitrogen. And it's typically best to put the negative charge on the more electronegative atom. Who's more electronegative, oxygen or nitrogen? Oxygen, and that's why this is the best possible Lewis structure we could have drawn. So this is a tough example. You had to know to put nitrogen in the center to start with your skeleton, and then you had to go through this rigmarole with formal charges, which is a big pain in the butt. Question? Thomas.
The most electronegative is the top right.
Yeah, towards who's the most electronegative? Fluorine. Fluorine. And the closer to fluorine, the more electronegative. And that's why oxygen's more electronegative than nitrogen, and again, this is the better structure. So SF4, this will be the first example where your wanted minus has method would not work. So this is going to be one of those octet rule exceptions that goes over the octet rule, that it has exceeds the octet rule. And that wanted minus has method doesn't work. But the method we've been using for every example still works every time. So who can make the most bonds? Sulfur. Notice fluorine can only make 1. Sulfur typically makes 2, but he can make a whole lot more if he goes over the octet rule, which he's allowed to. He's in the 3rd row or lower. So sulfur's going to win that battle. He goes in the middle. How many total valence electrons do I have here? Sulfur's got 6. Each of the fluorines has 7. 7 times 4 is 28 plus 6, 34. So lots and lots of electrons. We know sulfur goes in the middle. And where do I put electrons next at this point? Yeah, fill up the outside atoms. Again, you'll always have enough to fill them up. So I'm going to fill them all up, all the fluorines. They want a filled octet. Cool. At this point, we've used 8, 16, 24, 32. Do I have any electrons left? Yeah, and at this point, any electrons left always go on the central atom. So the 2 I have left to get to 34, just got to make room and put them on the central atom as a pair. Cool, and once you're done and you've run out of all your electrons, what do you ask yourself? Is the central atom happy? Is the central atom happy? Well, he's beyond happy, right? He's drunk with electrons. He's got 10, it's not 8. He's over the octet rule, but he's allowed to be. Why is he allowed to be again? 3rd row or lower. Sulfur's totally allowed. Sweet, that is the structure of SF4. He went over the octet rule. When the central atom goes over the octet rule, the wanted minus has method doesn't work, and you have to use this traditional method. But that's our structure for SF4. Cool? Any other questions about Lewis structures? Okay, got one more major example I want to cover with you before we move on. And that's going to be for an ion instead. So in this case, how many total valence electrons in this case? And you can't just add up the atoms. Because it has a negative charge, it has 1 extra that we'll have to add in as well. And so how many total electrons, or valence electrons I should say? 5 plus 18 plus 1. Good. 24. Who goes in the middle? Nitrogen goes in the middle. So in this case, I'll set up a structure. Nitrogen goes in the middle. And so here's the deal. Whenever you see an ion, when you make the final structure, you got to put that final structure in brackets and then put the charge in the upper right-hand corner. So it turns out we use these brackets in 2 situations. When we're doing the when we're doing the Lewis dot structure of an ion, or in an example involving resonance. And we're going to find out this is going to involve what we call resonance in a second as well. So it's going to doubly need brackets. But those are the 2 situations using brackets. Okay, so we put the nitrogen in the middle, set up single bonds everywhere. Where do I put electrons next? Outside atoms, fill them up. And at this point, I've used 8, 16, 24 electrons up. I've used them all. And so what do I ask myself? Yeah, nitrogen happy? No. How many more electrons does he need? Just 2. He just needs one of these guys to share with him. Well, here we got an issue. There are 3 different atoms that could possibly share with him. And they're all equivalent. And so in this case, this leads us to conclude that there are 3 equivalent structures we could draw. So let's make a little more room here. And so in this case, I could have this oxygen on the left be the one that shares. But I could have just as well had the oxygen down below be the one that shared instead. But yet again, I could have just as well have had the oxygen on the right be the one that got to share. They're all 3 equally likely. They're equivalent oxygens. Okay, so I get 3 alternative structures. We usually put a nice little double arrow in between all 3 structures. And then again, we call these resonance structures. We put them in one giant set of brackets. And we do that for resonance. And if it has a charge, you would use the brackets anyways, and you got to put the charge up there as well, in the upper right-hand corner. Okay, now here's the deal. We call this resonance. And resonance, let's do this in blue. These are 3 resonance structures, and resonance always involves what we refer to as delocalized electrons. Delocalized electrons. What does delocalized mean? If I were to say that I am delocalized, what's that now? Oh, it means I'm in more than one location at the same time. If I were delocalized, I could say, yeah, I'm teaching this class in here. I'm also in the next room over. I'm teaching another class right there right now too. I'm also in the room down the hall that way. I'm teaching another class in there right now. I'm in all 3 rooms at the same time. I would say that I'm delocalized. Notice everything that we ever touch with our hands is localized. It's in one location at one time, right? But in this case, it turns out that extra 2 electrons, in this structure, it looks like it's with the oxygen on the left. In this structure, it looks like those extra 2 electrons are in the bond between the oxygen down below. And in this structure, it looks like they're with the oxygen on the right. What it turns out, what really is going on here, what this structure really looks like, is it looks like that other bond is partially here, and partially here all the time. It is in all 3 locations simultaneously. And so in this case, because it's being shared between 3 locations, it's like there's an extra third of a bond there, an extra third of a bond there, and an extra third of a bond there. And so these are really like 1 1/3 bonds, but it's in all 3 locations at the same time. And again, we still can put this in brackets if you want and put a negative charge and stuff. We call this the resonance hybrid. That'll get more important when you take OChem. But the key is this. These structures never exist. We draw 3 of them, and if I say draw the Lewis structures, these are the correct Lewis structures. But what really exists in nature is this thing, is this average of these structures. And this gets tricky. We call this resonance, and when I hear the word resonance, I hear the word resonating. And when I hear resonating, I think of something resonating back and forth. And then I see that double arrow right there. I'm like, oh, it's flipping back and forth. And that's totally false. It's the biggest misconception in all of Gen Chem 1. These are not flipping back and forth, and not flipping back and forth here either. A lot of students think that, if I took a picture of this thing, maybe it looks like this, and then 5 seconds later, now it looks like this, and then 5 seconds later, now it looks like this. But again, this is completely false. It never looks exactly like this. It never looks exactly like this, and it never looks exactly like this. It always looks like the average of the structures all the time. So don't look at those double arrows and think it's flipping. It's not. Don't look at the word resonance and think resonating, because it's not. It always just looks like this all the time. The electrons are delocalized in many locations. Cool? You may get a question on the test that just says, which of the following can be drawn with 3 different resonance structures? Well, it's a multiple choice test, right? First thing I would do is just, if it's 3 different resonance structures, I'm going to look for something that has 3 atoms around the central atom to start off with. If I see something that's just like, HCl, it can't work, right? It's just 2 atoms, there's no way. So that's the first thing I would look for. And hopefully that narrows it down a little bit so that you don't have to draw Lewis structures for all the answer choices. But at some point, at the end of the day, you might have to draw at least a couple of different Lewis structures for those. But once I got as far as seeing that I had a nitrogen with 3 oxygens around it and one of them had to share, at that point would be sufficient to know that, oh yeah, that's going to be 3 resonance structures. That would have been the answer to the question of which of the following can be represented by 3 resonance structures. Cool. If you notice, because this is now a 1 1/3 bond, not a single bond, but it's not a double bond either. It's stronger than a single bond, which means it's shorter or longer? Shorter. So this bond right here is shorter than a nitrogen-oxygen single bond, but it's longer than a nitrogen-oxygen double bond. It's in between. And so this resonance thing can affect how long and how strong a bond is. It's going to make it some intermediate length and intermediate strength. In this case, somewhere in between a single and a double.